Okay, so some introductory mole mass particle conversions. So as we looked at in class, when converting between mass and moles, the value that you need to use is called the molar mass. It is the number of grams per 1 mole of a substance. Where do you find the molar mass? Well, the molar mass for every element is the same number as their atomic mass, and it's listed on the periodic table. So for carbon, its molar mass is 12.01. That means 1 mole of carbon weighs 12.01 grams. In other words, 12.01 grams per 1 mole. But in the IB, they would write it like this: 12.01 grams times mole to the minus 1. That means per mole. Now, we'll also see this presented as like a big capital M. So from now on, if I use the capital M, big M, that is a symbol that can be used to stand in for molar mass in equations. And so if we start with mass, the number of grams, we want to convert to moles, we end up needing to divide by the molar mass, and that gives us a value in moles. If we start with the number of moles and we want to know how many grams that is, we end up multiplying by the mass per mole. So multiplying by the molar mass. This little conversion chart that I just made up here can also be summarized into an equation. Moles gets the symbol N for number of moles. And if we want to find the moles of something, then we can do the mass of the something divided by big M, which is molar mass. So you'll hear me a lot in the course saying N equals M over M. And I know that's a silly sounding equation, but the M's are actually different. Little m is for mass, big M is for molar mass, and moles is N because M was clearly taken. So N is number of moles. You can also obviously rearrange that equation to solve for mass, and you can see that if you do moles times big M, molar mass, you get mass. So some people like to memorize equations. That can help them when solving. And there's different ways to do this. If you take the mass, like in this question, you start with 1.2 grams of carbon. And if I'm simply going to do moles is mass divided by molar mass, like the equation over here, then here's my mass, 1.2 grams, divided by the molar mass, 12, and that gets me 0.1 moles of carbon. Again, if you don't see the math there that we're dealing with 1/10, and so that's equivalent to 0.1 moles, you can also use scientific notation to make the math slightly easier. 12 divided by 12 is 1, and then there's the 10 to the minus 1. So there's your moles of carbon. Some people were also finding a ratio method as a helpful way to start. So the molar mass is really just a ratio. 12 grams equals 1 mole. So there's 12 grams per mole. So then that means there must be 1.2 grams per x moles. And so if we take away some of that rating, you can set it up like a ratio. That 1.2 over 12 must equal x over 0.1, and you can solve for this x, and that x will also equal 0.1 moles of carbon. So that's the basic premise, and we can keep on going here and try a few others. So how many moles of carbon are there? In 88 grams of carbon dioxide. So our mass is 88 grams. We've got to figure out our molar mass, which is a carbon, which weighs 12, plus 2 oxygens, each of which are 16 from, again, the periodic table. So 2 times 16 is 32, and so we've got a molar mass of 44 grams per mole. So if each mole weighs 44 grams, and I've got 88 grams, I've got twice that amount, so I've got an N value of 2. So 2 moles of CO2. So that's a way of talking about how many particles of CO2 I have. I have 2 moles of CO2, and so it might say I have 2 moles of CO2 molecules, because that's the kind of particle CO2 is. It's made of nonmetals, so I know it's covalent, and it's a small molecular formula. In the previous one, I could have said I have 0.1 moles of carbon atoms. Carbon is an element, so it's made of those little carbon atoms. Moving on, I have 0.36 grams of water. Water is H2O. Nonmetals, this is a molecule. Okay, so again, I've got a mass and divide it by the molar mass, and I'll get the moles. So the mass is 0.36 grams. the molar mass of water is 2 times hydrogen, which is 2 times 1, plus 16 for oxygen. I get 18 grams per mole. So I'm dividing 0.36 by 18 grams per mole. Now that looks really tricky at first until you remember that you can move decimal places, and you can get 36 times 10 to the minus 2 grams divided by 18 grams per mole. 36 divided by 18 is 2, and then you have times 10 to the minus 2 remaining, and that's going to be our number of moles of water. And again, it's a molecule, so I'd say I have that many moles of water molecules. Notice that anytime we figure out the number of moles, it's typically a fairly small number, like 0.1 or 2, or even 2 times 10 to the 2, which is 0.02. The number of moles is usually relatively small in our questions because moles represent lots of particles. Okay, now we have a couple that are in reverse. So if I can remember this equation, then I should be able to quickly rewrite it into moles times molar mass will give me mass. So I've got the moles, 0.010 moles of helium atoms. Helium's an element that exists as atoms. So sometimes they'll just include the type of particle in the question. It shouldn't throw you off. It's just a little bit of information. There's the number of moles. The molar mass of helium is a nice round 4 grams per mole, and I can see that when I multiply these, the mole part cancels and I'll end up in grams. It's a good double check. And so I end up with 0.04 grams of helium. Okay, last one. How many grams if I have 0.5 moles? So again, moles times molar mass, N times big M. It's going to give me little m, which is mass. This one is made of nitrogen, which weighs 14, and 3 times hydrogen, so in total I weigh 17. So 0.5 times 17, what's half of 17? Well, half of 16 is 8, plus half of the remaining 1 is 0.5, so I must have 8.5 grams of ammonia. Okay, moving on. When we work with particles, moles and particles, notice that it doesn't actually incorporate mass at all. Remember that the analogy for moles is that it's like bags of candy. So if I told you that you had 5 bags of candy, how many pieces is that? You wouldn't try to incorporate how heavy a bag of candy is. That wouldn't make any sense. Likewise, if I told you you had 600 pieces, how many bags is that? You wouldn't worry about how heavy the bags were. So we don't have to use the molar mass in a conversion between moles and particles, because mass is another way to talk about how much stuff we have. Moles and particles are different units. We're talking about how much we have of a substance. So when I start with moles, I'm going to multiply by Avogadro's number in order to get to particles. And if I want to get from particles to moles, I'm going to divide by Avogadro's number, 6 times 10 to the 23rd. So if you compare these two, notice that anytime you convert into moles, you divide and you get a smaller number. Whereas anytime you go out from moles, you end up multiplying. That's just a trick you can try to remember. You can also rearrange this, that you have moles times Avogadro's number equals the number of particles. So moles times Avogadro's number, which is n sub a, equals the number of particles, which is n sub p. And then we can rearrange that and also have the other way, which is moles equals the number of particles divided by Avogadro's number. So different ways to represent these as equations. Let's try 8 and 9. How many particles of iron 3 oxide? Notice it just used a generic term, particles, so we don't have to worry about what kind of particle this is. Technically it's ionic, so this would be a formula unit, but let's just leave it as particles. How many particles are there in 0.001 moles of it? Well, if I want to know the number of particles, NP, I need to do moles times Avogadro's number, and I'll get the number of particles. So I've got 0.0010 moles, and then Avogadro's number, 6 times 10 to the 23rd. Again, that's the number of particles per mole. And if you look at your units, the per mole and the mole will cancel and you'll be in particles. Now this might be tricky to calculate, as is without a calculator. So scientific notation, once again, can be helpful. So 1, 2, 3 spots over, this number can be rewritten as 1 times 10 to the minus 3. 1 times 6 is 6, and 10 to the minus 3 and 10 to the 23 is 10 to the 20, and that's the number of particles. The next question does it in reverse. If I want to know the moles of a substance, I need to do Np divided by Na, number of particles divided by Avogadro's number. Okay, so I've got 3.01 times 10 to the 21 particles. Now, if they use 3.01, it's because Avogadro's number is really 6.02 or 6.022 times 10 to the 23rd. And so in that case, I would include the 0.02. Most of the time you can just treat it like a 6 because you don't have a calculator. But if they're going to go ahead and use like a 0.01 or a 0.02, then you should do the same so that it matches and makes the math easier. And remember, on paper 1, there shouldn't be any tricky division. So if it's not easily divisible, then you're probably making a mistake. I can see right off the bat that 3.01 is half of 6.02. So I've got 0.5 here. But I still have these guys to deal with. And so 10 to the 21 on top, 10 to the 23 on bottom, that's 10 to the minus 2. I subtract exponents when I divide. So I've got 0.5 times 10 to the minus 2 moles, or I've got 5 times 10 to the minus 3 moles. That's the answer to 9. Okay, and finally we have some two-step conversions. This one, I'm starting in grams, and I want to know how many particles of calcium carbonate. Well, it's a two-step process. I first have to go from mass to moles, like I did on the first page of questions, and then once I know the moles, then I can figure out how many particles I have. So I just have to use my two equations back to back. So first I do moles is mass divided by molar mass, and then I'll do my moles times Avogadro's number, equals the number of particles. 0.010 grams. The molar mass of calcium carbonate rounded is 100. And so again, maybe this looks tricky, but you can move this decimal place over. So 1, 2, I get to 1. I'm going to keep going. 3, 4. If I move it 4 spots, I get 100 divided by 100. That's nice and easy. And on top was 10 to the minus 4 in order for me to do that. So the number of moles is 1 times 10 to the minus 4 moles. Avogadro's number is 6 times 10 to the 23. So I get 6 times 10 to the 19 particles as my answer to question 13. And our last homework question here, we got 1.8 times 10 to the 23 atoms. How many grams? So now I'm doing this in reverse. First, I'll use my particles divided by Avogadro's number to get moles, step 1. And then step 2, I'll do moles times molar mass to get mass. So I've got 1.8 times 10 to the 23 divided by 6 times 10 to the 23rd. Let's make it easier. 18 times 10 to the 22 divided by 6 times 10 to the 23rd. So now I've got 3 from 18 divided by 6 times 10 to the minus 1. That's my number of moles. That's the answer to step 1. And now I'm going to multiply by the molar mass. The molar mass of helium is a nice, easy 4 grams per mole. So I get 12 times 10 to the minus 1 grams, which is 1.2 grams.